good afternoon or evening or whatever. Today I wanted to do a couple of odds and ends to kind of finish up this section. And, and then we're going to go into integration, probably starting next week. I'm going to have to go pretty soon. Well, you have a little time before you go south, Snow. It's getting cold. Well, it's going to be 80 degrees today. You don't have to go south yet. I know, but it's getting late. Well, about the time we have our final exams, you should be taking off for the south. I know this will be your, what, third trip? No, my second, only my second. I'm not quite through yet. Well, and do you know where you're going yet? They had hurricanes down there. Well, I know the Gulf is a little dangerous. You could go further south. Venezuela? Well, yeah, maybe. Well, you will find your flock and you will have a good time, I promise. I'll be back. I know you'll be back, and we'll see you for quite a while now. Okay. What are you going to do today? Well, that's what I was going to talk about right now. So let's do that, and we can talk about migration a little later. There are a couple of things that I've gotten questions on, and I think we should talk about those a little bit. But let's consider this situation. We have a function that begins with two variables. Let's say we plot it in R3, and let's say we map back to two variables. And I'd like to think of this function in the following way. Let's label some variables here. We've been using S and T here. And let's use X, Y, and Z here. And let's use U and V as my variables here. And let's think of this function as being a function that will give you temperature and humidity. So U will be temperature, V will be humidity. And U of S and T will be a parametric function with two variables. It maps into three space. So its range will be a surface. So this is something like the surface of a mountain, or maybe the bottom of a lake, something like that. But this will be a surface. And then this function will give the temperature and the humidity on that surface. So let's call this the function f. And let's call this the function, let's see, we need a function of s and t. I guess we've been using r. Or maybe I'll use little g. So g is a function of s and t and spits out an x, a y, and a z. So each one of these is a function of s and t. So this is something like 3s plus 4t, s times t squared, and t e to the s. Something like this. This is fairly simple, but if we plot the range of this function, we get a surface in 3 dimensions. The temperature and humidity will be a function of 3-dimensional space. So given any point x, y, z, we will get a temperature function. I'll just make these up, they will be simple. So the temperature will be like x squared plus 2y squared plus 3z squared. And we'll get a humidity x, y, z. This is how to think about them. And so these are the two functions, and we want to look at the composition. F composed with g. This will be a function of s and t. And it will have two components. So it maps R2 into R2. So given an s and a t, it gives us back a temperature and a humidity. And what we are interested in is the derivative of this function as a function of s and t. And the chain rule tells us that this will be the derivative of f evaluated at g of s and t. So this means you have to plug in these formulas for x, y, and z's that naturally occur in this derivative, times the derivative of g with respect to s and t. So this is the chain rule at work, and I'd like to do this computation. Each one of these is a matrix. We'll compute those matrices, and this multiplication is matrix multiplication. So let's take a look. Two things to compute, f prime and g prime. So f prime as a function of x, y, and z. This means I haven't plugged in the formulas for x, y, and z yet, but this is easy to compute. This has three variables, x, y, and z, so there will be three columns to the derivative. And there are two formulas, a u and a v formula. So this is the u and this is the v, the variables here. And then this consists of the derivative of u with respect to x, derivative of v with respect to x, u with respect to y, v with respect to y, u with respect to z, v with respect to z. So that's the definition of that derivative. And let's do it for this particular example here. So here is u. With respect to x, you get 2x. With respect to y, you get 4y. And with respect to z, you get 6z. We did the first row. Here is v. With respect to x, you get yz. With respect to y, you get xz. And with respect to z, you get xy. So there is that derivative. If I plugged in g, and that will be the first part of the chain rule, is the plugging in of g. Then x gets replaced. Anytime you have an x, you replace it by 3s plus 4t. So here we have an x, so this would be 2 times 3s plus 4t. No x here and no x here. Here and here we have an x, so in either one of those places, we'll get a 3s plus 4t. And of course, there's more. In the first one, it was just 2x. And in this one down here, we have an x times z, so we have to multiply by the z, t, e to the s, t, e to the s. So that would be, this one is this one here. So when you find f prime of g of s, what you are doing is plugging in these formulas in the derivative of f for the x, y's, and z's. So we're going to keep this one up here. And now I'm going to compute g prime, s and t. Here we have two variables, s and t, and we have three formulas, an x, a y, and a z formula. So we're going to have 6 entries. This one will be the derivative of x with respect to x, s, derivative of y with respect to s, derivative of z with respect to s, x with respect to t, y with respect to t, z with respect to t. And in this particular example, the derivative of x with respect to s would be replaced by 3. The derivative of x with respect to t, this value would be replaced by 4. Derivative of y with respect to s would be t squared. Derivative of y with respect to t would be 2st, and so on. So these are, each one is a formula, a complicated arrangement. And if we multiply these two together, we're going to get the composite derivative. And I guess I will do that a little bit here. So f prime of x, y, z, let's do this, f composed with g prime of s and t. I'll put in an intermediate step where I don't substitute for those at first. So let's just do this step first and see what it is. So it means take this matrix, u sub x, u sub y, u sub z, v sub x, v sub y, v sub z, and multiply by this matrix, x sub s, x sub t, y sub s, y sub t, z sub s, z sub t. So the formulas we get when we multiply the whole thing out, this will be a 2 by 2 matrix. First row, first column is u sub x, x sub s, plus u sub y, y sub s, plus u sub z, z sub s. And then first row, second column, u sub x, x sub t, u sub y, plus u sub y, y sub t, plus u sub z, z sub t. And down here, v sub x, x sub s, plus v sub y, y sub s, plus v sub z, z sub s, comma. Same thing, but with t. So v sub x, x sub t, plus v sub y, y sub t, plus v sub z, z sub t. So this is what we get. And we have formulas for each one of these. The formula for x sub s, which I've erased here, but the formula for x sub s, you can plug in straight away. It will be in terms of s and t. The formula for u sub x will not be in terms of s and t. It doesn't come that way. It comes in terms of x, y's, and z's. So you have to plug in the x, y, z's from G in order to get the final answer. But these things are long and complicated. But here is the chain rule, how it works on such a function. The reason we're interested in this is, if you take a complicated situation, like we have, for example, with global warming, you're interested in temperatures and humidities, and you know that part of this is due to certain natural processes. Some of this is due to human activity, and there's an intermingling because all human activity depends on natural processes. And you actually want to know what changes we can make to make overall changes in the global warming. And so you want to know how much is due to natural part, how much is due, maybe this is the natural part, including the human, and how much is due to human activity. The actual situation is far more complicated than this, many more variables. But this is the idea of how this is used. This is why we are drilling ice cores in Antarctica and the Arctic and down in Greenland. This is why we're looking at the rates of melting, because we're interested in the derivative, warming, not warm, but warming. And we're interested to know how much of this is natural, how much of this is human, what can we control, what might be the consequences. Chain rule at work. Not by itself, but with statistics. A lot of science is involved, but certainly a lot of calculus is involved with all of these things too. Okay, I wanted to talk a little bit about directional derivatives also. So chain rule and directional derivatives. And a directional derivative is given by a function. So we're looking at graphs, and the directional derivative is the slope of the tangent surface. At a given point. In a given direction. So it's the slope of the tangent surface. And we've been looking at tangent planes, but this is also true for tangent lines, which end up to be a lot easier. It's also true for tangent three-dimensional surfaces when you're graphing functions of 3 dimensions in 4 space. This is always the slope of the tangent surface at a given point. And that's important to know because tangent surfaces are all like planes. From the linear algebra, the graphs of linear functions, linear transformations are flat, and they are nice to know. So, well, here we have it. So on this particular surface, this is a tangent surface. And at this given point, directions at this point out to the unit circle. This oblong thing is supposed to be a unit circle. And every arrow from this point out to the unit circle represents a direction. And so the slope of this plane in that direction, rise over run in that direction at this point, is going to be the directional derivative at that point. Because of the way flat surfaces work, there will be a direction where the slope is maximum, and exactly directly opposite is a direction where the slope is minimum. And the minimum is always exactly the negative of the maximum, because if rise over run is positive this way, rise over run will be negative the other way. And there will be a direction exactly halfway between where the slope is 0. So if I picture it like this, I'm trying to balance out this blue line so that the slope is 0. Here the slope is max. Rise over run looks like it's about 1. Here the slope is min, because the rise is actually a declination, so it's a down. So rise over run is exactly the opposite of what it is here. Now, there are, oh, by the way, for directions for us, we again mean unit directions, and that's why I drew this unit oblong thing here. And so there are a couple sort of facts about this. And the 2 facts I wanted to show you were that there is a max, and exactly the opposite of it is the min, and those are negatives of one another. Those 2 slopes are negatives of one another, and they occur in exactly negative directions. And halfway in between, 90 degrees from those directions, are where the graph is level. So let's take a picture. Let's think of that and figure out a couple of things about these directional derivatives. So if I give you a function of x and y, like x squared plus 3y squared. So if we actually look at the graph of this is a paraboloid. And at some point here, there is a tangent surface. It will be a tangent plane. And we know how to find the tangent, the slope of that tangent plane in the x direction and the slope in the y direction. So if we draw in the x and y axes here, and let's say that this is the point, well, let's just use 1, 1 maybe. So at this point 1, 1, what is the slope in the x direction? So to find the slope in the x direction, we can find the derivative here. So f prime of x and y is equal to 2x, 6y. So f prime of 1, 1 is 2, 6. The slope in the x direction is 2. Slope in the y direction is 6. Slope in the x direction is 2. Slope in the y direction is 6. And so it's easy to get the tangent plane. What I wanted to show you is that this maximal direction I was talking about and the maximal slope is also given by this derivative. It's given directly by this derivative. And let's take a look at that. So if we look at the derivative at any given point, and we take the dot product with any unit vector, this is a directional derivative. So directional derivative in, say, the u direction. So u is a unit vector. This would be the directional derivative 2x naught, 2y naught at the point x naught, y naught, dot u. And this is the length of the vector 2x naught. Well, this was not 2, this was 6. 6y naught. The length of that vector times the length of u, which is 1, times the cosine of the angle between them. And this length is just the Pythagorean theorem. It is the length of the derivative, which is 4x naught squared plus 36y naught squared times the cosine of theta. But theta is between 0 and 2 pi. The cosine is between 1 and minus 1. So this is less than or equal to the square root, and it's bigger than or equal to the square root. And it's maximum when this number is 1. So it's maximum when theta is 0. So the directional derivative is maximal where this direction is the same direction as the gradient. And it's minimal when theta is pi. And we saw this here, that it's maximal in one direction and exactly the opposite direction it'll be minimal, and the amount will be exactly the negative. So the maximal directional derivative is the length of the derivative, and it occurs in the direction of that gradient. So that's a nice thing to remember. I'm going to record it here. Maximal slope of tangent surface occurs when the direction is the same as the direction of the derivative. This is at a given point. Minimum slope occurs when the direction is the same as minus f prime of x naught. So this is a vector. It has a direction, unit vector in that direction. That's the direction of the maximal slope. This is a vector. The negative is a vector. It it has a direction, the unit vector in that direction, and that's where the minimum slope occurs. The max slope equals the length of the derivative, and the min slope equals the negative of that. All those are just a function of what happens with planes, linear surfaces. I think that's almost all. Finally, at theta equal pi over 2 or 3 pi over 2 from the gradient from the derivative, the slope is 0. And these are called the level directions. And so for a given derivative here, it's easy to find directions that are perpendicular to it, and in those directions, the slope is 0. So that's it. 2 small things from the end of this chapter. We'll work into integration. I'll give you a little practice sheet and some homework on this. See you tomorrow.